June 19, 1944. Imperial Japanese Navy Air Base, Tinian Island. Operations Briefing Room. Lieutenant Commander Saburo Sakai set down his pre-flight checklist and stared at the intelligence report that would shatter the myth of Japanese air superiority forever. The numbers were stark, terrifying, and would never be discussed in any official Imperial Navy briefing. Estimated American fighter strength, 12,000 F-6F Hellcat aircraft. Current Japanese Zero operational strength, 1,847 aircraft. What none of the assembled pilots knew was that this single intelligence assessment would reveal the mathematical impossibility of Japanese victory in the Pacific Air War, proving that the legendary Zero fighter that had dominated the skies for 3 years was about to become obsolete against an American industrial machine that was producing superior aircraft faster than Japan could train pilots to fly them. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The report contained aerial reconnaissance photographs, captured American documents, and statistical analysis that challenged every assumption about Japanese aviation superiority. While Japanese engineers had created the most maneuverable fighter aircraft in the world, American factories had perfected the mass production of faster, more heavily armed, and better protected fighters piloted by crews trained in numbers that Japanese flight schools could never hope to match. In the humid stillness of the briefing room, surrounded by photographs of American carrier task forces bristling with aircraft, Japan's most experienced fighter pilots would confront a reality that contradicted everything they believed about aerial combat, pilot skill, and the divine wind that was supposed to protect their homeland. The war they thought they were winning through superior flying ability was actually being lost in the factories of Detroit and the training fields of Texas, where American industry was producing victory through the brutal mathematics of overwhelming numerical superiority. By June 1944, the Pacific Air War had evolved from individual fighter duels into massive industrial competition where production capacity, pilot training throughput, and technological innovation determined outcomes more than individual courage or flying skill. The Japanese Zero fighter, which had achieved legendary status during the early months of the Pacific War, was facing systematic obsolescence against American aircraft designed specifically to exploit Zero weaknesses while incorporating lessons learned from 3 years of combat experience. The Mitsubishi A6M Zero had been conceived during the late 1930s as the ultimate expression of Japanese aviation philosophy: maximum maneuverability, exceptional range, and minimal weight achieved through elimination of protective features that reduced flight performance. The Zero could outmaneuver any Allied fighter in 1941, but this advantage had been purchased through design compromises that would prove fatal when confronted with American fighters designed for different combat priorities. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video. It means a lot to us. Now, back to the story. Japanese aviation doctrine emphasized individual pilot skill, aggressive tactics, and aircraft performance that maximized the effectiveness of highly trained aviators who had undergone years of intensive flight training. The Zero represented this philosophy perfectly, a fighter that was unforgiving to inexperienced pilots, but devastating in the hands of veterans who understood how to exploit its unique capabilities. American aviation doctrine had evolved to emphasize pilot survivability, aircraft durability, and tactical methods that could be executed successfully by quickly trained pilots flying aircraft with performance margins that compensated for limited experience. The F-6F Hellcat represented this alternative philosophy, a fighter designed to keep pilots alive while achieving tactical objectives through superior firepower, protection, and production numbers rather than exceptional maneuverability. The mathematical implications were becoming clear by 1944. Japan had trained approximately 15,000 fighter pilots since 1941, but combat losses, training accidents, and operational attrition had reduced experienced pilot strength to fewer than 3,000 aviators capable of effective combat operations. American pilot training programs were graduating 10,000 new fighter pilots annually, supported by advanced training aircraft, experienced instructors, and training facilities that could expand capacity as needed. But the most significant factor was production capacity. Japanese Zero production had totaled approximately 10,900 aircraft throughout the entire production run, with peak monthly output never exceeding 250 units. American Hellcat production would total 12,275 aircraft, with peak monthly production exceeding 600 units. The production mathematics guaranteed American numerical superiority that would overwhelm Japanese air strength regardless of individual pilot skill levels. Japanese fighter aircraft design reflected cultural and military values that prioritized individual excellence, tactical agility, and operational range over pilot protection and aircraft durability. The Zero embodied this philosophy through engineering decisions that maximized flight performance while accepting vulnerability characteristics that would prove catastrophic when confronted with American tactics designed to exploit those vulnerabilities. Jiro Horikoshi, the brilliant aeronautical engineer who designed the Zero, had approached the project with scientific precision that optimized aircraft performance within weight limitations imposed by available engine power and structural materials. Every component was designed to minimize weight while maximizing functionality, creating an aircraft that achieved unprecedented maneuverability through systematic elimination of non-essential features. The Zero's construction utilized lightweight aluminum alloys, minimal armor protection, and fuel systems that prioritized range over survivability. The aircraft could achieve 3,100-kilometer operational range, exceptional maneuverability at all altitude levels, and climb performance that exceeded most Allied fighters. But these advantages required design compromises that created vulnerabilities that American pilots would learn to exploit systematically. Most critically, the Zero lacked pilot armor, self-sealing fuel tanks, and robust construction that could absorb combat damage. The aircraft was designed for pilots who would avoid being hit rather than survive being shot. This philosophy worked effectively when Japanese pilots possessed superior training and experience, but became catastrophic as pilot quality declined due to accelerated training programs necessitated by combat losses. Commander Minoru Genda, the tactical genius who developed Japanese carrier aviation doctrine, understood that the Zero's design philosophy required pilots capable of avoiding enemy attacks through superior maneuvering rather than surviving attacks through aircraft protection. His tactical doctrine emphasized aggressive engagement, quick disengagement, and exploitation of superior climb and turn performance to achieve favorable combat positions. This tactical approach achieved devastating success during 1941 to 1942, when Japanese pilots possessed significant experience advantages over Allied aviators and could exploit Zero performance characteristics effectively. But tactical doctrine designed around pilot superiority became vulnerable when confronted with American training programs that were producing competent pilots in numbers that overwhelmed Japanese experience advantages through mathematical inevitability. While Japanese engineers focused on optimizing individual aircraft performance, American aviation industry had implemented mass production techniques combined with systematic combat analysis that produced fighters designed specifically to defeat Japanese aircraft through superior firepower, protection, and production quantities rather than exceptional maneuverability or range. Leroy Grumman's F6F Hellcat design philosophy represented a revolutionary approach to fighter aircraft development that emphasized practical combat effectiveness over theoretical performance optimization. The Hellcat incorporated lessons learned from 3 years of Pacific combat, analyzing Zero's strengths and weaknesses to create an aircraft optimized for defeating Japanese fighters through superior tactics enabled by better protection and firepower. The Hellcat design eliminated the Zero's primary advantages while exploiting its fundamental vulnerabilities. American engineers accepted reduced maneuverability in exchange for superior speed, climb rate at high altitude, and most importantly, pilot survivability features that allowed aviators to survive combat damage that would be fatal in Japanese aircraft. Most significantly, the Hellcat was designed from the beginning for mass production using American automotive manufacturing techniques. Standardized components could be manufactured by multiple suppliers. Assembly processes were designed for semi-skilled workers rather than precision craftsmen. Quality control standards emphasized functional effectiveness rather than precision manufacturing. Grumman Aircraft Engineering Corporation had organized production using assembly line techniques that maximized output while maintaining consistent quality standards. The Bethpage facility could produce 600 Hellcats monthly using production methods that could be replicated at additional facilities as needed. By contrast, Japanese Zero production remained constrained by traditional aircraft manufacturing methods that required skilled craftsmen and precision assembly techniques. The production mathematics were overwhelming. American industry was producing Hellcats faster than Japan could train pilots to fly Zeros. Grumman was delivering new aircraft at rates that exceeded total Japanese pilot training output, creating numerical advantages that would prove decisive regardless of individual aircraft or pilot performance comparisons. American pilot training programs complemented industrial production through systematic instruction methods that prepared competent fighter pilots in 18 months rather than the 4 to 5 years required by Japanese training programs. Training aircraft, fuel supplies, and instructor availability were essentially unlimited, allowing continuous expansion of pilot production to match aircraft manufacturing output. Direct technical comparison between the Zero and Hellcat revealed fundamental differences in design philosophy that reflected broader strategic approaches to fighter aircraft development and deployment. The comparison demonstrated how American engineering had systematically analyzed Japanese aircraft capabilities and developed countermeasures that exploited Zero vulnerabilities while negating Zero advantages. The Mitsubishi A6M Zero, the most advanced production variant, achieved maximum speed of 565 km per hour, service ceiling of 11,740 meters, and operational range exceeding 3,000 kilometers. The aircraft weighed 2,733 kilograms loaded and was armed with two 20mm cannons and two 7.7mm machine guns. Most importantly, the Zero could achieve sustained turning performance that no Allied fighter could match in horizontal maneuvering combat. The Grumman F6F5 Hellcat achieved maximum speed of 629 km per hour, service ceiling of 11,370 meters, and operational range of 1,755 kilometers. The aircraft weighed 5,714 kilograms loaded and was armed with six .50 caliber machine guns that provided superior firepower concentration compared with Zero armament. The Hellcat incorporated pilot armor, self-sealing fuel tanks, and robust construction that allowed survival of combat damage that would destroy Japanese aircraft. The performance comparison revealed that American engineers had deliberately sacrificed maneuverability and range to achieve advantages in speed, firepower, and survivability that were more valuable in the tactical environment of 1943 to 1944. The Hellcat was faster than the Zero at all altitude levels, could climb more rapidly above 6,000 meters, and possessed overwhelming firepower advantages that made brief combat engagements decisive. Most critically, the Hellcats' protection systems allowed American pilots to survive combat mistakes that would be fatal in Japanese aircraft. Pilot armor stopped rifle-caliber projectiles that could kill Zero pilots. Self-sealing fuel tanks prevented fires that destroyed Japanese aircraft. Robust construction allowed Hellcats to return to base with combat damage that would cause zero structural failure. Navy test pilot Lieutenant Commander Frederick Trapnell conducted comparative flight evaluations that quantified Hellcat advantages over captured Zero aircraft. His test reports revealed that the Hellcat possessed decisive advantages in high-speed combat, diving attacks, and sustained high-altitude operations. The Zero retained advantages only in low-speed horizontal maneuvering that competent American pilots could avoid through proper tactical discipline. The technical analysis confirmed that American aircraft design had evolved beyond the limitations that had constrained early Pacific War fighters. The Hellcat represented systematic application of combat experience to create aircraft optimized for defeating specific enemy capabilities rather than achieving theoretical performance excellence. Japanese aviation industry faced mathematical constraints that prevented effective response to American aircraft production, regardless of organizational efficiency improvements or resource allocation adjustments. The analysis revealed fundamental inadequacies in Japanese industrial capacity that could not be solved through tactical innovation or pilot training improvements. Mitsubishi Zero production had peaked at approximately 200 aircraft monthly during 1943, utilizing maximum industrial capacity available for fighter aircraft manufacturing. Expanding production beyond this level would require resources needed for bomber production, naval construction, and ground equipment manufacturing. Total Japanese fighter production capacity across all types totaled approximately 500 aircraft monthly under optimal conditions. American Hellcat production exceeded 600 aircraft monthly from the Grumman facility alone, with additional fighter production from other manufacturers totaling over 2,000 aircraft monthly across all types. American production capacity was expanding while Japanese capacity remained constrained by strategic bombing, resource shortages, and skilled labor limitations. Strategic materials analysis revealed additional constraints that made Japanese production expansion impossible. Aluminum requirements for aircraft construction exceeded available supplies when multiplied across planned production numbers. Engine production required specialized alloys that were increasingly scarce due to transportation disruption and resource allocation conflicts. Production engineer Yoshitoshi Tokugawa had calculated that maintaining current Zero production levels required strategic materials that would be depleted within 6 months at current consumption rates. Alternative materials and recycling programs could not provide sufficient quantities to sustain production while maintaining performance standards necessary for combat effectiveness. Quality control standards were being compromised to maintain production schedules, resulting in aircraft delivery with mechanical problems that reduced operational effectiveness. Field reports indicated declining Zero reliability due to manufacturing shortcuts necessitated by resource shortages and accelerated production requirements. The mathematical equation was becoming unsolvable. Japanese aviation required aircraft production capacity that exceeded available industrial resources while confronting enemies whose production capacity appeared unlimited by resource constraints or facility limitations. The assessment conference that would determine Japanese aviation strategy for the remainder of the Pacific War occurred on July 15, 1944, in the secure briefing room at Combined Fleet Headquarters. Present were Admiral Soemu Toyoda, Commander-in-Chief Combined Fleet, Vice Admiral Takijiro Onishi, Commander of 1st Air Fleet, and Captain Minoru Genda, Senior Aviation Staff Officer, along with intelligence analysts who had compiled comprehensive assessments of Japanese aviation capabilities versus American air power. The conference had been called to develop strategies for maintaining Japanese air superiority against increasing American numerical advantages. But the statistical evidence presented during the meeting demonstrated that existing problems reflected fundamental industrial and tactical inadequacies that could not be solved through organizational adjustments or operational modifications. Admiral Toyota opened the discussion by presenting casualty statistics from recent Pacific battles that quantified the scope of the crisis facing Japanese aviation. Zero losses during June and July had totaled 847 aircraft, while zero production during the same period had delivered 398 new aircraft to operational units. The deficit of 449 aircraft represented irreplaceable depletion of Japanese fighter strength that could not be compensated by existing production capacity. Vice Admiral Onishi's operational assessment confirmed that Japanese aviation was losing the mathematical war of attrition that would determine Pacific air superiority. American aircraft losses were being replaced faster than they were being inflicted, while Japanese losses represented permanent strength reduction that was approaching critical levels for sustained operations. Captain Genda presented tactical analyses that revealed the technical obsolescence of Zero fighter capabilities against evolved American tactics and superior aircraft performance. The Zero's traditional advantages in maneuverability were being negated by American pilots who could exploit speed and firepower superiority through disciplined tactical methods. Intelligence Officer Commander Yahachi Tanabe presented production comparisons that demonstrated the mathematical impossibility of maintaining Japanese air strength against American industrial capacity. Current American fighter production exceeded total Japanese aircraft production across all categories by ratios approaching 4-to-1, with American production continuing to increase while Japanese production declined due to strategic bombing and resource depletion. The most sobering aspect of the analysis was recognition that production and training disparities were accelerating rather than stabilizing. American industrial and training capacity was expanding while Japanese capacity remained constrained by limitations that could not be overcome through resource reallocation or organizational efficiency improvements. As the senior officers concluded their conference, each understood that they had just witnessed the mathematical proof of Japanese aviation defeat in the Pacific War. The legendary Zero fighter that had dominated Pacific skies for 3 years was becoming obsolete not through technical inferiority, but through industrial mathematics that favored mass production of adequate aircraft over limited production of excellent aircraft. The 12,000 Hellcats represented more than numerical superiority. They represented a fundamental shift in aviation warfare where industrial capacity determined outcomes more than individual pilot skill or aircraft maneuverability. American factories were producing victory through systematic application of combat lessons learned from 3 years of fighting against Japanese aviation. But the full implications of aviation obsolescence extended beyond immediate tactical considerations. Japanese aviation strategy had been based on assumptions about pilot quality and aircraft performance that were being invalidated by American industrial capacity to produce competent pilots and superior aircraft in quantities that overwhelmed individual excellence through mathematical inevitability. The real air war was being fought in American factories and training facilities, where industrial workers and flight instructors were determining Pacific victory through production methods that Japanese industry could not match. The Zero had been designed for a different kind of war, one where individual excellence could compensate for numerical disadvantage. That war was ending, and Japan was about to discover the true meaning of American industrial power. The mathematical equation was becoming clear. 1,847 Zeros could not defeat 12,000 Hellcats, regardless of pilot skill or tactical innovation. The age of Japanese air superiority was over. American pilot training programs had achieved industrial scale that produced competent aviators faster than Japanese programs could graduate experienced pilots, creating cumulative advantages that would determine Pacific air superiority through mathematical inevitability rather than individual skill superiority. Naval Air Training Command had organized instruction systems that could process 15,000 student pilots annually through standardized curricula designed to produce consistent performance rather than exceptional individual capability. Training emphasized formation flying, gunnery accuracy, and tactical discipline that maximized Hellcat advantages while minimizing dependence on exceptional pilot skill. Training aircraft availability was essentially unlimited. American training programs utilized 8,000 aircraft dedicated exclusively to pilot instruction, including advanced trainers that closely approximated combat aircraft performance characteristics. Students could accumulate 300 flight hours before graduating to operational assignments, compared with 150 hours in accelerated Japanese programs. Commander Jimmy Thoch had developed tactical training methods that taught American pilots to exploit Hellcat performance advantages systematically. The thatch-weave defensive formation utilized superior Hellcat firepower and protection to defeat Zero maneuvering advantages through coordinated attacks that overwhelmed individual Japanese pilots regardless of skill level. Fuel availability for training operations was unlimited, allowing continuous flight instruction that maximized student learning without resource constraints. Japanese training programs were increasingly limited by fuel shortages that reduced flight hours and prevented adequate preparation for combat conditions. Instructor availability reflected American training capacity advantages. Experienced combat pilots were rotated to training assignments where they could transfer tactical knowledge to new pilots while recovering from operational stress. Japanese programs lacked instructor reserves necessary for systematic knowledge transfer, forcing combat units to train replacement pilots during operations. The mathematical advantage was overwhelming. American training programs were graduating pilots at rates that exceeded Japanese losses plus expansion requirements, while Japanese programs could barely replace combat casualties. American pilot strength was increasing, while Japanese pilot strength was declining through irreversible attrition. While Japanese aviation struggled with declining aircraft availability and pilot shortages, American aircraft production had achieved levels that transformed the fundamental nature of Pacific air warfare. The scale of American manufacturing created surplus capacity that allowed tactical flexibility impossible when aircraft were scarce and irreplaceable. Grumman Aircraft Corporation had revolutionized fighter production through assembly line techniques that produced Hellcats at rates exceeding one aircraft per working day from multiple production facilities. The Bethpage factory alone employed 25,000 workers operating in 3 shifts to maintain continuous production schedules that delivered 674 aircraft in peak monthly output during 1944. Production efficiency had been achieved through standardization of components, tooling designed for rapid assembly, and quality control systems that maintained performance standards while maximizing output. Unlike Japanese aircraft production, which required skilled craftsmen for precision assembly, American production utilized semi-skilled workers, performing repetitive operations that could be mastered quickly and performed consistently. Production manager Jake Swerble had implemented manufacturing techniques derived from automotive industry experience, treating aircraft assembly as an industrial process rather than precision craftsmanship. Component manufacturing was distributed across multiple suppliers, allowing parallel production that reduced bottlenecks and accelerated delivery schedules. The mathematical result was aircraft availability that eliminated traditional constraints on aviation operations. American carriers could launch maximum sorties without conserving aircraft for future missions. Pilots could engage in aggressive tactics without concern for aircraft preservation. Maintenance crews could cannibalize damaged aircraft for spare parts because replacement aircraft were continuously available. By contrast, Japanese aircraft production remained constrained by traditional methods that emphasized individual aircraft quality over production quantity. Zero manufacturing required 18,000 man-hours per aircraft compared with 10,000 man-hours for Hellcat production. Japanese quality control standards prevented the shortcuts that American production used to achieve rapid delivery without significantly compromising performance. The production disparity was accelerating rather than stabilizing. American aircraft manufacturing was expanding through new facilities and increased line speeds, while Japanese production declined due to strategic bombing, resource shortages, and skilled worker depletion. Every month increased the numerical advantage that would prove decisive in sustained operations. August 15, 1944. USS Essex, Pacific Ocean, Flight Deck Operations. Lieutenant Commander David McCampbell adjusted his oxygen mask and watched the 200th Hellcat of the morning launch from the carrier deck, part of an air armada that would have been impossible to imagine 3 years earlier. The mathematics of American air power had become overwhelming. Task Force 38 alone could launch 1,200 aircraft in a single strike, more fighters than the entire remaining Japanese Air Force could deploy across all Pacific theaters. What Japanese aviation commanders had failed to understand was that American industrial capacity wasn't just producing superior aircraft, it was creating an entirely new form of aerial warfare, where numerical concentration made individual pilot skill irrelevant through mathematical inevitability. The flight deck of USS Essex represented the ultimate expression of American naval aviation. 90 aircraft operating from a single vessel, supported by maintenance crews, spare parts, fuel supplies, and replacement pilots that could sustain continuous operations indefinitely. Similar decks on 24 other fleet carriers were launching identical numbers of aircraft, creating concentrated air power that exceeded Japanese capabilities by ratios that challenged fundamental assumptions about aviation warfare. But the most devastating aspect of American air supremacy wasn't the individual superiority of Hellcat fighters. It was the systematic application of industrial warfare principles to aviation combat. American factories weren't just producing aircraft, they were manufacturing victory through mathematical certainties that Japanese aviation could not overcome regardless of tactical innovation or individual heroism. American aviation tactics had evolved beyond individual aircraft performance to emphasize formation coordination, systematic target engagement, and operational procedures that maximized numerical advantages while minimizing exposure to Japanese strengths in individual combat. Fighter tactics development had shifted from dogfighting emphasis to coordinated attacks that utilized Hellcat's speed and firepower advantages through disciplined formation flying. American pilots were trained to avoid prolonged maneuvering combat where zero agility provided advantages, instead utilizing high-speed attacks that exploited Hellcat performance superiority. The boom and zoom tactical method allowed Hellcat pilots to engage Japanese aircraft at advantageous speeds and altitudes while maintaining escape options if combat conditions became unfavorable. American pilots could choose engagement terms through superior aircraft performance, forcing Japanese pilots to accept disadvantageous combat conditions or avoid engagement entirely. Coordinated bomber escort techniques had been developed to maximize fighter effectiveness while accomplishing primary mission objectives. Hellcat formations provided layered defense that could engage intercepting Japanese fighters while maintaining bomber protection through superior numbers and coordinated tactics. Radio communication systems allowed real-time tactical coordination that was impossible with Japanese aircraft lacking adequate communication equipment. American formations could adjust tactics, redistribute forces, and coordinate attacks through voice communication that provided decisive advantages in complex combat situations. Lieutenant Commander John Blackburn had developed training programs that emphasized tactical discipline over individual heroics. American pilots were taught to maintain formation integrity, conserve ammunition for high-probability shots, and utilize mutual support rather than individual excellence to achieve tactical objectives. Target prioritization had been systematized to maximize strategic impact rather than individual kill scores. American pilots were trained to attack Japanese bombers first, then engage fighters in coordinated formations that utilized numerical superiority to overwhelm individual Japanese pilots through concentrated firepower. The tactical evolution reflected systematic analysis of combat effectiveness rather than traditional aviation culture. American aviation had become an industrial process optimized for achieving strategic objectives through mathematical certainties rather than individual pilot excellence.
Facing inevitable defeat in conventional air combat, Japanese aviation developed kamikaze tactics that reflected desperation rather than strategic innovation, acknowledging that traditional fighter combat could no longer achieve meaningful results against overwhelming American numerical and technological superiority. Vice Admiral Takejiro Onishi had implemented kamikaze operations as recognition that Japanese aviation lacked conventional capability to inflict significant damage on American naval forces. Individual aircraft could achieve tactical impact through suicide attacks that eliminated the pilot skill requirements that Japanese training programs could no longer fulfill adequately. The mathematics of kamikaze operations were brutal, but logical from Japanese perspectives. Conventional attacks achieved hit rates of 2 to 3% against American naval targets, while exposing aircraft and pilots to defensive fire that usually resulted in losses without corresponding damage infliction. Kamikaze attacks achieved hit rates of 15 to 20% while guaranteeing pilot and aircraft loss regardless of tactical success. Captain Rikihei Inoguchi had calculated that kamikaze operations could inflict damage rates that exceeded conventional attacks by factors of 5 to 7 times, making suicide tactics mathematically superior when resources were limited and pilot quality was declining. The analysis assumed that pilot lives were expendable resources rather than irreplaceable assets. Training for kamikaze operations required minimal flight instruction compared with conventional combat training. Pilots needed only basic flying skills and navigation capability rather than advanced combat techniques that required months of instruction and operational experience. Training time was reduced from 18 months to 6 weeks, allowing rapid expansion of pilot availability. Aircraft requirements were simplified through elimination of armor protection, advanced weaponry, and equipment necessary for pilot survival. Obsolete aircraft could be converted for kamikaze operations, extending the useful life of airframes that were no longer competitive in conventional combat. Even training aircraft could be utilized for suicide attacks. The strategic impact was limited despite tactical success in individual attacks. Kamikaze operations inflicted damage on American naval forces but could not prevent continued American offensive operations or reduce the fundamental numerical advantages that determined Pacific air superiority. Suicide tactics represented admission of defeat rather than path to victory.
American naval forces developed systematic countermeasures against kamikaze attacks that demonstrated industrial warfare's capacity to solve tactical problems through technological solutions and numerical superiority rather than individual skill or tactical innovation. Radar-directed fighter interception had been developed to provide early warning and coordinated response against kamikaze formations. American radar coverage could detect approaching Japanese aircraft at ranges exceeding 150 kilometers, allowing fighter deployment with sufficient advance warning to intercept attacks before reaching naval formations. Fighter Combat Air Patrols, CAP, were organized in multiple layers that could engage kamikaze aircraft at different distances from protected naval forces. Outer CAP stations operated at maximum radar detection ranges, while inner CAP provided final defense against aircraft penetrating initial interception lines. Anti-aircraft artillery coordination had been systematized to provide concentrated firepower against kamikaze aircraft approaching naval formations. Fire control systems allowed coordinated engagement by multiple ships, creating defensive barriers that achieved hit rates exceeding 60% against individual attacking aircraft. Damage control procedures had been developed to minimize impact from successful kamikaze hits. American naval architecture included compartmentalization, firefighting systems, and repair capabilities that could restore operational capability after kamikaze damage that would disable less robust vessels. Admiral Frederick Sherman had implemented tactical formations that maximized defensive firepower while maintaining operational flexibility. Carrier task groups were organized with escort vessels positioned to provide overlapping anti-aircraft coverage while maintaining maneuverability necessary for flight operations. The most significant countermeasure was numerical superiority that made kamikaze operations strategically ineffective despite tactical success. American naval forces could absorb kamikaze damage while maintaining operational capability through replacement vessels, repair capacity, and surplus resources that eliminated strategic impact from individual attacks. Mathematical analysis revealed that kamikaze operations were achieving tactical success at unsustainable rates for strategic effectiveness. Japanese aviation was depleting remaining pilot and aircraft resources faster than kamikaze attacks could inflict corresponding damage on American operational capability. The final phase of Pacific air warfare had become purely mathematical, with American industrial capacity determining outcomes through numerical advantages that eliminated tactical considerations as significant factors in strategic success. Japanese aviation faced mathematical certainties that could not be overcome through innovation, determination, or tactical excellence. American aircraft production during 1944 totaled 96,000 military aircraft across all types, including 12,000 fighters delivered to Pacific theater operations. Production rates were accelerating through facility expansion and process improvement that continued increasing output while maintaining quality standards adequate for combat effectiveness. War Production Board statistics revealed aircraft manufacturing capacity that exceeded wartime requirements by significant margins, allowing surplus production that could compensate for combat losses while building strategic reserves for extended operations. American industry was producing aircraft faster than they could be deployed effectively, creating abundance that eliminated traditional resource constraints. Japanese aircraft production during 1944 totaled approximately 16,000 military aircraft across all types, with production declining monthly due to strategic bombing, resource depletion, and industrial facility damage. Quality control standards were being compromised to maintain production schedules, resulting in aircraft delivery with reduced reliability and performance capability. Pilot training mathematics were equally decisive.
American programs graduated 10,000 new pilots during 1944, while Japanese programs graduated fewer than 3,000 pilots with significantly reduced training standards. American pilot strength was increasing, while Japanese pilot strength was decreasing through irreplaceable combat losses. Strategic materials analysis revealed that Japanese aviation faced resource constraints that made production sustainability impossible regardless of organizational efficiency improvements. Aluminum supplies were depleted to critical levels. Aviation fuel allocation was insufficient for both training and operational requirements. Engine production was limited by strategic materials that were no longer available in adequate quantities. American resource availability appeared unlimited for aviation purposes. Steel production exceeded aircraft requirements by substantial margins. Aluminum production was expanding through new facilities and process improvements. Aviation fuel supply was adequate for maximum operational tempo, plus extensive training programs without rationing or allocation restrictions. By late 1944, American aviation technology had advanced beyond Japanese development capability, creating performance gaps that could not be closed through tactical innovation or pilot skill improvements. The technological advantage complemented numerical superiority to create overwhelming air combat effectiveness. Next-generation American fighters were entering service with performance characteristics that exceeded Zero capabilities by substantial margins. The F-4U Corsair achieved maximum speeds of 671 km per hour while maintaining superior firepower and protection systems. The P-51 Mustang provided long-range escort capability that eliminated Japanese bomber operational effectiveness. Engine technology had advanced through systematic development programs that produced power plants superior to Japanese designs in reliability, power output, and operational altitude performance. The Pratt & Whitney R2800 engine provided 2,000 horsepower compared with 1,130 horsepower from the Nakajima Sakai engine powering late Model Zeros. Aviation electronics had been developed to provide tactical advantages impossible with Japanese technology. American aircraft incorporated radar systems, advanced radio communication equipment, and navigation aids that enhanced combat effectiveness while reducing pilot workload and training requirements. Weapons technology had evolved to maximize combat effectiveness through superior firepower concentration and ammunition characteristics. American .50 caliber machine guns provided greater range, accuracy, and destructive power compared with Japanese 20mm cannons, while American ammunition included armor-piercing and incendiary rounds optimized for aircraft destruction. Maintenance technology had been systematized to maximize aircraft availability through standardized procedures, diagnostic equipment, and replacement parts supply that could maintain operational readiness rates exceeding 85%. Japanese maintenance capability was declining due to spare parts shortages and trained mechanic depletion. The technological advantage was accelerating rather than stabilizing. American research and development programs were producing continuous improvements, while Japanese development capability was constrained by resource limitations and facility damage from strategic bombing.
Japanese aviation strategy had collapsed under mathematical realities that rendered traditional concepts about air combat obsolete. The strategic framework that had guided Japanese aviation development was proving inadequate for industrial warfare, where production capacity determined outcomes more than tactical excellence. Combined fleet aviation strength had been reduced to fewer than 1,500 operational aircraft by October 1944, with pilot quality declining due to accelerated training programs that could not provide adequate preparation for combat conditions. Effective combat strength was estimated at fewer than 800 aircraft capable of sustained operations. American Pacific Fleet aviation strength exceeded 8,000 operational aircraft supported by maintenance, supply, and replacement systems that could sustain maximum operational tempo indefinitely. Reserve aircraft availability allowed continuous operations without conservation requirements or operational restrictions. Operational tempo had become a decisive factor that favored American forces equipped with unlimited aircraft and pilot availability. American aviation could maintain continuous offensive operations, while Japanese aviation was forced to conserve resources for defensive operations that were becoming increasingly ineffective. Base vulnerability had eliminated Japanese operational flexibility, as American air power could attack any Japanese aviation facility within combat radius of carrier task forces or land-based aircraft. Japanese aviation was forced to operate from increasingly remote bases that reduced operational effectiveness while failing to provide security from American attack capability. Fuel shortages were limiting Japanese aviation operations to minimal training and essential combat missions. Pilot proficiency was declining due to inadequate flight hours, while operational effectiveness was reduced through fuel conservation requirements that prevented maximum aircraft performance utilization. The strategic situation had become hopeless through mathematical inevitability. Japanese aviation faced American air power that was expanding continuously, while Japanese capability was contracting through irreversible resource depletion and facility destruction.
November 20th, 1944. Imperial Japanese Navy Ministry, Tokyo. Emergency Aviation Conference. The conference that would acknowledge the complete failure of Japanese aviation strategy brought together the surviving senior officers responsible for naval air operations. Present were Admiral Soemo Toyoda, Vice Admiral Takejiro Onishi, Captain Minoru Genda, and intelligence officers who had compiled the final assessment of Japanese aviation capability versus American air power. The statistical evidence was unequivocal. Japanese aviation had been eliminated as a strategic factor in Pacific operations. Operational aircraft strength had been reduced to levels insufficient for defending Japanese territory, much less conducting offensive operations against American forces. Pilot quality had declined to standards that prevented effective combat against experienced American aviators flying superior aircraft. American aviation strength had reached levels that exceeded Japanese peak capability by factors of 8 to 10 times, with production continuing at rates that guaranteed unlimited sustainability. American pilot training was producing aviators faster than Japanese aviation could inflict casualties, creating permanent advantages that would increase until Japanese surrender. Captain Genda presented the final tactical assessment that acknowledged Zero fighter obsolescence. Individual Zero performance remained adequate for specific combat conditions, but American numerical superiority eliminated opportunities for Japanese pilots to exploit maneuvering advantages. American tactics had evolved to negate Zero strengths while maximizing Hellcat advantages through disciplined formation flying and coordinated attacks. Vice Admiral Onishi confirmed that kamikaze operations represented the only remaining option for inflicting casualties on American forces, but acknowledged that suicide tactics could not prevent American victory or protect Japanese territory from invasion. Kamikaze attacks would deplete remaining pilot resources while achieving limited strategic impact. The mathematical conclusion was inescapable. Japanese aviation had lost the industrial war that determined air superiority in the Pacific. The legendary Zero fighter would be remembered for early war achievements, but 1944 had proven that industrial capacity was more important than individual aircraft excellence in determining aviation warfare outcomes. The Zero's obsolescence represented more than tactical defeat. It demonstrated how industrial warfare had transformed military aviation from individual combat skill to systematic application of manufacturing capacity. The Pacific Air War had become a contest between Japanese craftsmanship and American industrial mathematics, with mathematical certainty determining the outcome. Post-war analysis revealed that Japanese Zero production totaled 10,939 aircraft throughout the entire program, while American Hellcat production reached 12,275 aircraft in less than 4 years. The production comparison demonstrated American industrial advantages that determined air warfare outcomes more than individual aircraft or pilot performance.
Combat effectiveness statistics showed that Hellcats achieved kill ratios of 19-1 against Japanese aircraft during 1944 to 1945, reflecting not just individual aircraft superiority, but systematic advantages in pilot training, tactical development, and operational support that Japanese aviation could not match with limited resources. The strategic lesson was fundamental. Modern warfare belonged to nations capable of sustaining industrial production while maintaining technological advancement. Individual excellence could achieve tactical success, but could not overcome systematic disadvantages in production capacity, training throughput, and resource availability. American aviation industry had demonstrated that mass production techniques could maintain quality standards while achieving production rates that overwhelmed enemies relying on traditional manufacturing methods. The Hellcat represented systematic application of combat experience to create aircraft optimized for defeating specific enemy capabilities. Japanese aviation industry had demonstrated the limitations of precision manufacturing when confronted with enemies possessing superior industrial capacity. Zero design excellence could not compensate for production constraints that limited aircraft availability to levels insufficient for sustained operations against numerically superior forces. In the depths of American factories and training facilities, the mathematical equations that determined Pacific air superiority had been calculated by industrial workers and flight instructors rather than combat pilots. The 12,000 Hellcats represented industrial mathematics applied to aviation warfare, creating numerical certainties that individual pilot skill could not overcome. The Zero's obsolescence reflected fundamental changes in warfare, where industrial capacity determined outcomes more than traditional military virtues. Nations that could produce adequate equipment in overwhelming quantities would defeat nations that produced excellent equipment in limited quantities, regardless of individual unit superiority or tactical innovation. Admiral Chester Nimitz's assessment proved prophetic. The Japanese built the world's finest fighter aircraft, but we built enough good fighter aircraft to make their finest irrelevant. Industrial mathematics had overwhelmed individual excellence through systematic application of American manufacturing capability. The Pacific Air War had ended not through decisive aerial battles, but through mathematical inevitability. American factories had produced victory, while Japanese craftsmanship had created masterpieces that were numerically insignificant. In total war, industrial capacity proved more decisive than aeronautical excellence. The legendary Zero Fighter War would be remembered for its early dominance, but history would record that it became obsolete not through technical inferiority, but through mathematical defeat by an enemy whose industrial capacity could produce superior aircraft in quantities that rendered individual excellence strategically irrelevant.